The observatory was silent, except for the occasional electronic hum of machinery. For decades, this place had been dedicated to solving one of the greatest mysteries in all of physics. The scientists had gathered mountains of data, built increasingly sophisticated models, and developed entire careers trying to find the answer. And now, on this otherwise unremarkable evening, everything had changed. The terminals displayed results that couldn't be ignored. After nearly a century of searching, the dark matter mystery was finally being cracked open. Not with a triumphant shout, but with the quiet, persistent efforts of thousands of scientists across generations who had each added one small piece to an impossibly complex puzzle. Our story begins not with the current breakthrough, but with a Dutch astronomer peering through telescopes nearly a century ago. In the early 1930s, Fritz Zwicky was studying the Coma galaxy cluster, a dense collection of over 1,000 galaxies, some 321 million light-years away from Earth. As he observed the movement of galaxies within the cluster, he noticed something peculiar. They were moving far too quickly. According to our understanding of gravity and the visible matter in these galaxies, they should have been flung apart. The cluster simply didn't have enough visible mass to generate the gravitational force needed to hold itself together. And yet, despite the mathematics suggesting the cluster should have dispersed long ago, it remained intact, defying the known laws of physics. Zwicky proposed a radical idea. Perhaps most of the matter in the universe was invisible, what he termed dunkle materiae, or dark matter. This mysterious substance wouldn't interact with light or other electromagnetic radiation, making it impossible to see directly. But it would exert gravitational force, potentially explaining why cosmic structures behaved as if they contained more mass than we could observe. This was an extraordinary claim, one that would fundamentally change our understanding of the universe. And like many revolutionary ideas, it was largely ignored for decades. It wasn't until the 1970s that Zwicky's idea gained serious traction. Astronomer Vera Rubin observed that stars at the edges of spiral galaxies were orbiting just as quickly as those near the center, a finding that contradicted our understanding of orbital mechanics. According to Newton's laws, stars at the outer edges should orbit more slowly, just as the outer planets in our solar system take longer to complete their journeys around the Sun. The fact that they didn't suggested there was more mass in these galaxies than we could see, invisible matter exerting gravitational pull. And so, dark matter transitioned from fringe theory to mainstream scientific puzzle. The hunt was on. But what exactly were scientists looking for? That's the peculiar challenge of dark matter. We can observe its gravitational effects, but it doesn't interact with light or other electromagnetic radiation. It passes through normal matter without colliding. It doesn't clump together to form dark stars or dark planets. It doesn't become hot or cold in ways we can detect. It is, in almost every way that matters for detection, invisible. And yet, according to our calculations, it makes up approximately 85% of all matter in the universe. We are, in essence, the minority in our own cosmos. Visible matter is the outlier, the exception, the cosmic rounding error. And so, Generation Z of physicists have dedicated their careers to developing ways to detect something that is, by definition, undetectable by conventional means. They've built elaborate experiments deep underground to shield them from cosmic radiation. They've repurposed particle accelerators to search for dark matter particles. They've used satellites to map the gravitational influence of dark matter across the entire observable universe. They've developed mathematical models and intricate simulations to predict its behavior. And they've proposed dozens of candidate particles that might explain what dark matter actually is. The most promising candidate for many years was the WIMP, weakly interacting massive particle. These hypothetical particles would have mass, allowing them to exert gravitational influence, but would interact only very weakly with normal matter via the weak nuclear force. They'd be passing through us constantly, billions of them streaming through your body every second. But because they interact so rarely with normal matter, you'd never notice. Finding evidence of these particles became one of the central quests of modern physics. Researchers built elaborate detection chambers, often placed deep underground to shield them from cosmic rays and other background radiation. These detectors typically contained ultra-pure materials that might, on very rare occasions, interact with a passing dark matter particle. The LUX experiment, for example, used a tank filled with 370 kilograms of liquid xenon, cooled to -108 degrees Celsius. If a dark matter particle were to collide with a xenon atom, it would produce a tiny flash of light and a few free electrons, signals that sophisticated sensors might detect. Similar experiments were built around the world, each hoping to be the first to catch definitive evidence of dark matter. And yet, despite decades of increasingly sensitive experiments, no conclusive evidence of WIMPs emerged. Time after time, new detectors with greater sensitivity would begin operations. Scientists would wait with bated breath, and nothing. The universe maintained its stubborn silence on the nature of dark matter. Some began to wonder if we were looking for the wrong thing entirely. Indeed, as the years passed, other candidates emerged. Perhaps dark matter wasn't made of massive particles at all. Maybe it consisted of axions, hypothetical particles proposed to solve problems in quantum chromodynamics that would have very little mass but might exist in enormous numbers. Or perhaps it was primordial black holes. Tiny black holes formed in the early universe that would be too small to detect directly, but could exert the gravitational effects we observe. Or sterile neutrinos, hypothetical particles related to the standard neutrinos, but unable to interact via the weak nuclear force. Each theory had its advocates, its own detection strategies, and its own challenges. Meanwhile, some physicists began to question whether dark matter existed at all. Perhaps our theories of gravity were simply wrong. Modified Newtonian dynamics, or MUN, propose that gravity behaves differently at the vast scales of galaxies than it does in our solar system. This would explain the unusual rotation of galaxies without requiring any exotic matter. But Mondi struggled to explain other observations where dark matter seemed necessary, such as gravitational lensing, the bending of light from distant objects as it passes through the gravitational field of closer objects. And so, the scientific community found itself at an impasse. The evidence for something beyond our standard model was overwhelming, but what that something might be remained elusive. Each new experiment, each new observation, each new theory added pieces to the puzzle, but the complete picture remained frustratingly out of reach. Dark matter became the greatest detective story in science. We knew a mystery existed. We had plenty of clues, but the culprit remained at large. This brings us to the breakthrough that changed everything. Like many scientific revolutions, it didn't come from where most expected. While large international collaborations were building ever more sensitive particle detectors, a different approach was quietly gaining momentum. Instead of trying to detect dark matter directly, what if we could understand it by observing its effects on the structure of the universe? For years, cosmologists had been mapping the distribution of dark matter throughout the cosmos by observing how light from distant galaxies is bent by gravitational lensing. These maps revealed a cosmic web of dark matter, with dense concentrations in galaxy clusters connected by filaments stretching across millions of light-years. But these were static images, snapshots of the present-day universe. What if we could See how this web evolved over time? The breakthrough came from a combination of new observational techniques and advanced computational modeling. By studying galaxies at different distances from Earth, and therefore at different points in cosmic history due to the finite speed of light, scientists could observe how the dark matter web has evolved over billions of years. At the same time, powerful supercomputers allowed researchers to run sophisticated simulations of how different types of dark matter would behave over cosmic timescales. What emerged from this approach was unexpected. The data revealed subtle patterns in how dark matter clumps together and how these clumps evolve over time. These patterns didn't match the predictions for WIMPs or Axions or any of the other leading candidates. Instead, they pointed to something far stranger. Dark matter appeared to have properties of both particles and fields, behaving sometimes as discrete entities and sometimes as a continuous medium pervading space. The implications were profound. Dark matter couldn't be understood within the framework of the standard model of particle physics. It wasn't simply a new particle waiting to be discovered. It represented something more fundamental, a new state of matter, perhaps even a new force of nature that interacted with gravity in ways we hadn't anticipated. The universe wasn't just a little more complicated than we thought. It was operating according to rules we hadn't even considered. The breakthrough didn't come from a single experiment or observation, but from the convergence of multiple lines of evidence: astronomical observations of galaxy dynamics and the cosmic, microwave background, gravitational wave detections that revealed how dark matter influences the mergers of black holes, and finally, a new generation of particle physics experiments designed not to detect dark matter directly, but to probe the subtle ways it might interact with the quantum vacuum. This approach finally yielded results. In experiments conducted deep underground, scientists detected minute variations in the quantum field, variations that couldn't be explained by any known particle or force. These variations appeared to be resonances created by dark matter particles passing through the quantum vacuum, like ripples in a pond. They weren't direct detections of dark matter itself, but rather echoes of its passage through the fabric of reality. What made these results compelling was their consistency with the astronomical observations and computer simulations. For the first time, observations at the quantum scale aligned with observations at the cosmic scale. The dark matter model that emerged was elegant in its simplicity, yet revolutionary in its implications. Dark matter, it turns out, isn't a single type of particle. It's a quantum field that permeates the universe, similar in some ways to the Higgs field, but with crucial differences. Under certain conditions, this field can condense into particle-like excitations, not true particles in the conventional sense, but localized concentrations of field energy that behave like particles. This dual nature explains why dark matter behaves sometimes like discrete particles and sometimes like a continuous medium. Moreover, this dark matter field interacts with gravity in a way that no other known field does. It doesn't just respond to gravitational fields. It actively shapes them, creating a feedback loop that explains the distribution of dark matter we observe in the cosmos. This property also explains why dark matter doesn't clump into dense objects like stars. The field naturally resists compression beyond a certain density. This new understanding of dark matter has profound implications for our understanding of the universe's history and future. It suggests that dark matter played a far more active role in the formation of cosmic structures than previously thought. Rather than passively providing gravitational scaffolding, dark matter actively guided the evolution of galaxies and galaxy clusters through its complex field dynamics. It also means we need to reconsider our understanding of the early universe. The standard model of cosmology assumes dark matter consists of simple particles that influence the formation of the first stars and galaxies through gravity alone. If dark matter is actually a complex quantum field with its own internal dynamics, the story of cosmic evolution becomes far richer and more intricate. Perhaps most excitingly, this breakthrough opens new avenues for detection and even utilization of dark matter. If dark matter is a quantum field that interacts with the vacuum in detectable ways, we might be able to develop technologies that can sense and perhaps even manipulate this field. The physics would be extraordinarily challenging, but no more so than quantum mechanics or general relativity were when first discovered. But what does this mean for the average person? Why should anyone who isn't a physicist care about the nature of dark matter? The answer lies in how fundamental discoveries have transformed human civilization throughout history. When Einstein published his theory of general relativity, few could have predicted that it would eventually be essential for GPS satellites to function correctly. When quantum mechanics was being developed, no one anticipated its role in creating computers and smartphones. Similarly, a true understanding of dark matter could lead to technologies we can barely imagine today. If we can detect and interact with the dark matter field, we might develop new ways to navigate space, generate energy, or even communicate across vast distances. The gap between theoretical physics and practical applications can be long, but it has been bridged many times before. Moreover, there's something profoundly important about understanding the universe we inhabit. For most of human history, we believed that the world was made of the same stuff we could see and touch. Now we know that visible matter, the stars, planets, and galaxies that seem so substantial, is just a minor component of reality. The universe is primarily composed of entities we cannot directly perceive: dark matter and dark energy. Coming to terms with this reality changes our place in the cosmos. We are not just small in a vast universe. We are made of minority constituents in a cosmos dominated by something fundamentally different from ourselves. This realization is humbling, but also inspiring. It reminds us how much remains to be discovered, how the greatest mysteries can persist for generations before yielding to human ingenuity and persistence. The dark matter breakthrough didn't come as a flash of insight from a lone genius, but from the collective efforts of thousands of scientists working across disciplines and decades. It's a testament to what we can achieve when we combine curiosity with collaboration, when we're willing to question our assumptions and follow the evidence wherever it leads. And so, as we stand on the threshold of this new understanding of dark matter, we're reminded of how science constantly reshapes our view of reality. The universe is not just stranger than we imagine. It's stranger than we can imagine. But with each breakthrough, our imagination expands. What seems incomprehensible today may become the foundation of tomorrow's technologies and philosophies. The dark matter mystery isn't completely solved, of course. Science doesn't work that way. Each answer brings new questions. Each discovery reveals new horizons of ignorance. We now have a framework for understanding dark matter, but filling in the details will occupy physicists for generations to come. What is the exact structure of the dark matter field? How does it interact with the Higgs field and other quantum fields? Could it be related to dark energy, the even more mysterious force driving the accelerating expansion of the universe? These questions await future breakthroughs, future generations of scientists with tools and concepts we can't yet envision. But for now, we can celebrate this moment, when humanity took a significant step forward in understanding the invisible architecture of reality. When we illuminated a little more of the darkness that surrounds us, not with light, but with the power of human reason and collective endeavor. The observatory that witnessed the breakthrough is no longer silent. It's buzzing with activity as researchers analyze the data, refine their models, and design new experiments to explore the implications of their discovery. The dark matter mystery hasn't ended. It's evolved. And as it has so many times throughout history, Our understanding of the universe has expanded, revealing a reality more complex, more elegant, and more wondrous than we had imagined. And so, the quest continues, as it always has, and always will, driven by that most fundamental of human qualities, the desire to understand.